So it's a great pleasure for me to introduce Professor Daniel Ferris. Professor Ferris is a Robert Adenbaum Professor at University of Florida in the Department of Mechanical Engineering and in the Crayton Pruitt family Department of Biomedical Engineering. A worldwide expert in many fields across biomechanics, robotics, neural control, locomotion. He received the Bachelor of Science from University of Central Florida, a Master from University of Miami, a Ph.D. from UC Berkeley. So his research focuses on many aspects of human locomotion, in particular biomechanics, neural control, and I believe what he's going to talk about today are things related to human-machine interaction. And I can keep talking a lot about his research. He has received many honors and awards. I think this year he became Fellow of the American Society of Biomechanics, but he received other important distinctions in the past. He's editor-in-chief of IEEE Transaction Neural System and Rehabilitation and Rehabilitation Engineering. He received other awards. I think I don't want to steal too much time from his presentation. Thanks a lot, Professor Ferris, for being here.
Thank you so much for the invitation. I appreciate it. And if you have any questions as I'm going through, feel free to stop and interrupt me. We're a small enough group that we can have more discussion than me lecturing if people have questions about what I'm talking about. So let's start off. I grew up reading comic books from my older siblings, my older brothers, and to me, the idea of Iron Man with robotic exoskeletons and Cyborg with bionic limb replacements and Professor Xavier and his Cerebro, which was a mind-computer interface, always fascinated me. And they sort of led me through my education to the point that I realized, well, maybe actually studying those and trying to come up with ways to build those would be good. And so my lab really focuses on those three things right now: robotic exoskeletons, bionic prostheses, and brain-computer interfaces. And it really comes down to merging humans and machines. How do you take technology and allow it to increase the capabilities of a human, especially when it regards to movement? How do you enable an amputee to be able to have better mobility, or to let a aging grandparent go to Disney World and hang out with their grandkid all day long without getting tired? And that's really what drives the laboratory. If you look historically at when engineers first started building any of these types of devices for assisting human movement, so let's say a bionic limb or a robotic exoskeleton to help you walk, really the mindset was, well, let's take robotics and what we know and build the machine and then somehow get a command out of the human to make it do what we want it to do. And that was sort of the idea of how to make it work. And it followed a lot of understanding about things like driving a car, right? Like if you want to increase the mobility of a human, maybe not just give them a car, give them something they can control that makes them move. And that was sort of the scenario for a lot of first and second generation exoskeletons and prostheses. But I would argue it really has failed us, that approach. And we need a different perspective if we want to make the technology better. And that sort of perspective is that you have a human and you have to understand how the human functions. What are the equations of motion and the control laws that dictate how a human moves? Then build your machine with the idea that you want to be a symbiotic relationship with a human, not just receive commands and do what it's supposed to, but that there's a mechanical transfer of both information and power between a human and machine, and that you have an electrical transfer of information and power between the human and the machine. And without being able to write out equations that dictate the theoretical framework of how this symbiotic relationship functions, we're never going to really get to the point where we can build a truly bionic human that is allowing them to move as a single system. One way to think about it is this framework that Chilel and Beer had proposed in 1997 when they talked about the brain has a body, and if you want to understand neuroscience, you need to understand how the body functions, and you need to understand the environment that it interacts with. So here CNS represents the central nervous system, and that it transfers information to and for the body, and that the body then interacts with the environment. And all of this is not just electrical and information, but it's also mechanical. And this combination is a good framework for thinking about how we try to understand how humans control their motion. And I'll give you a couple of examples from recent studies without going into a ton of detail. So we have an ongoing study where we're trying to understand why elderly people struggle with their mobility. And so what we've done is dealt with this outside framework of the environment. We've built a treadmill that has uneven terrain because we've added these hard foam pucks onto the treadmill surface, and we can control it to make it difficult to walk on, but controlling it by saying we're changing the level of unevenness. So we really have a parametric variation in the surface difficulty level. And then we can use EEG to actually monitor the brain dynamics and IMUs to measure the motion of the individual so that we can study how the nervous system has to adapt the body to control in this varying environment. Another example is great. You have this person who's walking and running on a treadmill, but how do they respond when you give them environmental obstacles to deal with? So what happens if you throw an obstacle onto the surface and they have to observe that it's there and then adjust their mechanics? And so we can use EEG to look at what parts of the brain first notice that there's an obstacle and how they respond and how that scales with walking speed and running speed. Alternatively, instead of dealing with this outside layer of the environment, you can change the body dynamics. So we also do things like look at how people walk with robotic exoskeletons. In this case, they have an ankle exoskeleton that makes their ankle much stronger than they normally would be. And they're controlling it through an EMG interface, so it's very physiologically normal control. But all of a sudden, their ankle is much stronger. So by perturbing that body dynamic, we can look at how the human actually responds to, the nervous system responds to controlling it. And I would argue similarly, studying amputees walking with bionic prostheses is another way to perturb the body dynamics to see how the nervous system is adapting its control. And this can give us insight that allows us to have better knowledge of the human before you ever design the technology, because really our technology is such that we can build hardware, but we're not getting a good symbiotic relationship that makes it worthwhile for the human to use it. So if we look at robotic exoskeletons, there are a ton of devices on the market and at universities. The limitation is not hardware. The limitation is controllers and symbiotic relationship. Everything on the top row is a device designed to help a healthy, intact individual do more than what they normally could. Whether it be a soldier trying to carry heavy loads, whether it's a grandmother going to Disney World to keep up with their kids, whether it's an astronaut who is now having to move about the Martian surface after microgravity. All of these are essentially designed for a neurologically intact human. These bottom ones are designed for therapeutic function or assistive technology function. So can you help somebody with a spinal cord injury or stroke learn to walk again or to replace their wheelchair? When you look at the range of control approaches that people have used, a lot of them use state-based control with intrinsic sensing. And what do I mean by this? It means let me put sensors that either sense kinematics or kinetics onto the human or onto the device that senses the cyclic nature of how you're walking, and then use the last few steps to predict how you're going to move in the next few steps. That actually works quite well if you're moving at a constant speed on flat level terrain for a long duration. What it doesn't do well is imagine you're in a crowded subway where people are trying to get in and out of a new subway train and you have to go up and down steps and stop and start and go left and right. Your next few steps probably don't reflect the last few steps as well anymore. So how do you get feed forward information out of the brain? Some people think that EEG may be the route. Some people think that EMG, putting electrode sensors on and sensing at the periphery, may be the best approach. Others are trying cortical implants. Can we cut inside the skull and implant chips that record from many, 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 many neurons and send that signal to an exoskeleton? I would argue that in the long term, it's going to be some sort of hybrid controller. Take advantage of any type of signal you can use and then design a controller that prioritizes which of those signals is most important. We really are not that different. Think about, you normally walk through your house by combining vestibular information and proprioceptive and cutaneous information and vision. But when you get up in the middle of the night and it's dark, you can't see, you can still walk through your house. You just don't rely on the visual input as much, and you rely on those other sensory signals. So why not rely on a range of different signals and then prioritize when they have high robust signal to noise ratio? So over the last 25 years or so, my lab has been building different types of robotic exoskeletons and controllers and putting them on people to see how they manipulate, how they walk. Many times we measure oxygen consumption and carbon dioxide production because we want to know how it helps them metabolically. Art Kuo, professor at Calgary, loves to say, humans are really good at the principle of laziness. They use as little amount of energy as they can get away with. And so if we can help somebody walk, you will usually see it in a reduction in metabolic cost. We film them to monitor how they're moving, their kinematics. We have them walk on force treadmills and force platforms to measure how they're pushing against the ground. We measure their muscle activity. To see how they recruit their muscles. And we can do things like electrically stimulate their nerves to look at reflex modulation. And then more recently, we've added in high-density electroencephalography to actually look at brain dynamics. And why is that a really important thing? It can give you really good sensory information back about the processes going on in the brain. I'll give you an example. I could have each of you walk on a balance beam and film you and know when you lose balance and step off. And your kinematics will tell that. The kinetics and EMG will give me some insight. But with EEG, you can actually see when the brain is processing the sensory information, when it realizes that they're falling. Things like that are only possible when you use brain dynamic measurements with EEG. One of our initial exoskeletons was
I
designed
have a
for
question,
running.
if I may.
Sure, go ahead.
So, is there a way to do fMRI as well?
fMRI has a much slower time constant. So you can use fMRI. Generally, you have to have people laying down or sitting down to get an fMRI measure. And it only gives you a signal over 2 or 3 seconds at best. So if you're looking at something about how fast do they respond in a single gait cycle, EEG is a much better signal to look at than fMRI.
Okay, thank you.
Yeah, and anybody watching, feel free to interrupt. I'm happy to answer those questions as we go. Okay, one of our initial exoskeletons was built by one of my PhD students looking at running. And the idea was, let's imagine you're recovering from an ACL injury or some other knee injury, and you want to get back to running, but you don't want as high of joint contact force in the knee, and you're trying to reduce the quadriceps muscle activity. He built an exoskeleton that's essentially sort of like a big giant running prosthesis in parallel with your leg. So it's like the prostheses that athletes use for running 100, 200, 300 meters, but it's in parallel with the leg. And so it stores and returns energy and reduces the forces on the knee. It actually works very well, but it also increased metabolic cost considerably by 50%. Because you're adding all this extra added mass and inertia that you have to deal with during the swing phase. So it's just like putting extra weights on your foot and having to pull it forward every time. So while one system may do what you would wanted, your goal of reducing knee contact forces, it may have detrimental consequences, like requiring greater torques at the hip and requiring greater metabolic cost. We've tested a bunch of different other systems. Sometimes we work with companies. This is a device from the company Betinia out of Canada. It's designed for soldiers to carry heavy loads. One of the initial tests was in a laboratory walking on a flat surface and then doing an inclined surface and trying to understand how it assists with locomotion. But out in the real world, you end up with lots of different variety. I mentioned earlier about walking through a subway. Imagine walking through a subway where you're dodging people moving around you, dealing with escalators and steps and ducking into a subway before the door closes and stopping, and then dealing with external perturbations of the subway speeding up and slowing down. Or natural terrain. You have rocky terrain and slopes that you have to deal with. You have puddles. Maybe you have stepping stones that you have to put your foot. All of that is not really well predicted by your last 2 or 3 steps. You have to sort of adapt on the fly. We've used things like all-terrain treadmills to look at how people adjust and trying to get signals about how they're walking to transmit. But we also take our exoskeletons outdoors. Here's an example of one of our experiments, walking up and down in an arboretum, trying to see how it relates to different types of terrain and how well it works. A lot of these devices are very good under very strenuous situations. If you imagine having a 50-pound load, you're climbing up a hill. Yeah, they're usually pretty good at that. But when you say walking on flat level surface, without extra weight, they're not as good at that. And so trying to come up with designs that allow you to be successful in many tasks and environments is one of the keys to having a successful technology. And it turns out human experiments take a lot of effort and time. So that's what this little cartoon is meant to elaborate, is you can build your device, have somebody try it out in lots of different scenarios. You don't always know how they're going to use it, and trying to get all that information can take many life cycles, and grad students can get a little frustrated with it. So how can we speed up that prototyping and testing? One way that one of my PhD students, Sebastian, came up with is to design a mechanical phantom limb. What this is a robotic limb that you can put an exoskeleton on for testing before you ever get to human testing. He made a lower limb, phantom limb that's made out of ballistics gel. If you've ever watched the show Mythbusters, then you're very familiar with ballistics gel. They use it all the time. But we built a leg out of it and 3D printed bones that can go together, and that is controlled by a robot. So we can test out various devices. And here's his specific exoskeleton. This is a 3D printed lightweight robotic exoskeleton for children with cerebral palsy. Especially when you get to certain populations that you want to benefit. Bringing in a lot of children who have neurological disabilities may not be the best way to do your testing until you've got a pretty good idea it's going to work. And so by doing prototyping on this phantom limb, we could go through many generations and test out how energy was transferred back and forth from the exoskeleton and to the human user in a way that would be beneficial. And so many of the design criteria changed as we went through iterations. When we think about the neural control transfer of information, one way to think about how humans control their bodies is you have this desired movement in your head of what you want to achieve. Then you send it through an inverse model in your brain, which then withdraws what the muscle activation signals need to be, sends that to the muscles, produces the movement. You get sensory feedback, which you compare with your predicted sensory feedback. So at the same time, you send the muscle commands to your muscles, you send a copy of it, the afferent's copy, to a forward model in your brain, which predicts the motion and predicts the sensory feedback. so you can do a comparison of is that information matching up before you adapt your inverse model. Daniel Wolpert, who's now at Columbia University, had a ton of studies which really showed the processes involved in this loop. The simple example is it's really hard to tickle yourself. You can take a feather and try to tickle yourself, but you don't really respond the same way as if somebody else takes a feather to your skin. And that's because you're really good at predicting the sensory feedback that you're going to get when you're doing the tickling. He had a really cool experiment where he had a robotic arm interface between one hand and the tickling. And when you do that and put a time lag of about 300 milliseconds, all of a sudden you start feeling ticklish again. So when you add in time delays between what you're doing and what the sensory information is that you're getting, then all of a sudden it feels like somebody else is doing it. It feels like an outside agent. So the key is, how do we take this framework and adapt it to a bionic prosthesis or a robotic exoskeleton? And over 25 years of testing, I would argue that you form a secondary model, inverse model, and a secondary forward model, the more you use an exoskeleton or a prosthesis, so that you learn to flip between your normal inverse body model to your inverse model that includes the exoskeleton, so that you can adjust for different muscle commands, then compare the expected sensory information in a way that matches the context. And we've done a number of experiments which seem to suggest this is a process that takes on the order of hours or days of practice, and it's not something you learn within a few minutes. One of the ways that we like to get a feed-forward command signal is actually to use EMG. This is soleus electromyography. So we put electrodes on the skin recording the muscle activity, send it through a control signal interface that generates a proportional signal to something like a pressure regulator that can control a pneumatic muscle, so that the more you recruit your own muscle, your own soleus, the more assistance you get in, say, an ankle exoskeleton. When we first started doing this many years ago, back in the early 2000s when I was at Michigan, Greg Sawicki and Keith Gordon were two PhD students of mine that did a lot of studies. You can see this is Keith going up on his toes. Those are the electrodes. This is the burst of EMG activity. And this is an undergrad holding the ankle exoskeleton, showing you that it responds in real time. The electromechanical delay between this electrical signal and the mechanical assistance matches the biological muscles. There's really not a delay as the nervous system thinks of it. Then we started this out by recruiting a bunch of healthy undergrads and asking them to walk on a treadmill and turning on their exoskeleton.
It's recording.
And you'll notice they have a hard time with all of a sudden their ankle being extra strong. Their model does not let them know how to control that exoskeleton until they get practice and do it. If you look at her, she's stepping on her toes. She's got what's known as a Aquinas gait in clinical terms, because she's just getting too much torque and power out of her ankle. In about 30 minutes, she comes back with a normal walking pattern. I'll show you now at the end of 30 minutes. She's got a normal walking pattern, but we're going to take away the power. And all of a sudden she has a stutter step. She's moving left to right over the treadmill, and she says, wow, your leg feels heavier. Because in that 30 minutes, you basically turn down your own muscle activation. Do you have another question, Alessandro, or no?
Yes. So my question is this. So this individual did not have any problems at the ankle, right?
I'm sorry, one more time?
So the individual in the experiment did not have any problem at the ankle, right?
Nope.
Got it. So I'm wondering, like, did you guys make any experiments on athletes, people which do something like long jump or that type of thing?
Yeah, and so there are a lot of people that are actually trying to say, if I put this on you, can all of a sudden, can you jump higher? Does it actually give you added a jump? And people are starting to show that it does work, but it puts a lot of stress on the exoskeleton, and a lot of them break really quickly. So we really can't build robust devices that can last up to the demands of the human body.
So the reason for which I'm asking is this one. Now, I'm not an expert at all, but just asking the question. I heard that people which use doping have they have long-term effects, namely that if they train themselves on some substances, then it's like the brain is trained at a certain level, a certain speed, and then they have an effect even when they are not on any illegal substance. Okay. Now I'm wondering if there are athletes which train themselves on these type of things like that they don't break and something like that, and then they have long-term effects. So that's the question, right?
Yeah, so it's a really good question that we should know the answer to eventually. I would say that we probably don't know yet the answer to it because we don't have people using a lot of these exoskeletons for long term. We're still sort of in the setup where we can do laboratory tests really well, but doing it for chronic terms is difficult. There are some people wary that if you use an exoskeleton too much, maybe your muscles will get weak because you won't use the exoskeleton. You won't use them as much. But we're just not at the point where people really can answer those questions. Okay. So recently we just published a bunch of papers in collaboration with a DeFi exoskeleton. So DeFi is a spinoff from MIT. This is a portable electromechanical ankle exoskeleton. Rachel Heiber was a former Ph.D. student that had put a controller on that is also based on EMG. And she looked at whether or not it would provide assistance and change the way they walk outside in lots of scenarios. The take-home message is, yes, you can learn to control this. But if you don't get enough power out of it, it may not actually benefit you for agility wise. So we were really curious as, if you take this outside to where you have lots of different conditions, or you put them on a treadmill that has uneven terrain, does it really make them behave better? And a lot of the times the answer is no. And so when they try to test soldiers that really want to use it out in the real world conditions, if it doesn't help them, then they're not really going to be convinced to do it. So we've got a bunch of papers that came out recently on this, and I'm happy to talk about them at the end if you want. But let me move on to prostheses for a minute. There are many bionic robotic prostheses that are being built for the lower limbs now. Because the batteries are smaller, the actuators are smaller, the electronics are smaller, they're more powerful actuators. So there are devices on the market. Most of them do use intrinsic sensing for state machine control. So that is basically what I already talked about, where the prosthesis has sensors which tries to guess what you want to do based on the last few steps. It controls the impedance, position, or force that changes the mechanics of the prosthesis. And then the only interaction from the amputee to the prosthesis is mechanical. And then the ground interacts with the prosthesis. But if you have like a decrease in step height, then the prosthesis doesn't know that you're stepping down. And so it's a problem. How do you get information out of the user that has vision to know how it changes what it wants to do? One way to do that is actually to embed electrodes inside the socket so that you record the muscle activity in the residual limb of muscles. So this is two different amputees, transtibial amputees. You can see they have very different residual limb structure. This one has very robust muscles, this one not so much, you would say. But in truth, they still send electrical signals to those muscles that are in the residual limb. They just don't do anything. They're tied off. You can intercept those signals with electrodes placed inside the socket and actually use it as a command signal for the exoskeleton or for the prosthesis. So our initial attempts was with a pneumatic prosthesis shown here. Here's an example of an individual with a lower limb amputation learning how to control her own ankle by activating those muscles that don't do anything anymore. She could go up on her toes. She could dance the tango. She could flex and extend. She could walk. If there's a puddle in front of her, she could push off more for the next step than what she did last step because she's in control of it. It worked quite well, to tell you the truth, with the pneumatic system. It was the first lower limb prosthesis we know of that was a proportional command control on demand. And it was very interesting listening to all the subjects that we tested because they would give us insight as to what they liked and what they didn't. For example, it's about the same weight as the other prosthesis, but it looks and feels more natural walking than the other. Once I figure out what it's doing, I can figure out how to operate it, and it picks up really quickly what I want it to do. Friday's session was extraordinary for me. Just the brief experience of moving a limb I had not had contact with since 1970 was a total treat. Picture Christmas for a 5-year-old. Very pure, great stuff. It most likely wasn't extremely obvious, but both of my eyes were tearing. They were very emotionally attached to the bionic prosthesis that they could control because they were adopting it into their body schema. They felt like it was actually their ankle because they could control it and move it whenever they wanted. And I think it gets back to the use of the internal models. If you can control a device by saying, I want to push more or less, and you're in control with no lag, it makes it really easy to feel like it's your limb again. So Nicole Stafford's finishing up a PhD working on this bionic prosthesis under EMG control. And tests so far have been very similar. They feel very attached to the prosthesis. In this case, because it's electromechanical, they can walk with it out and about. They don't need a compressed air tank to deliver it. But they are showing signs of embodiment of the device because they're in control of it. Nicole's papers are about ready to be submitted. She's going to graduate this spring. One of the things we've learned is they like the controller, but power is a limiting factor. This device can only get up to a certain amount of power, and I think if we could control it at a higher power output, it would be really helpful.
I think
Okay,
Sushir
so
has raised his hand. I think Sushir has raised his hand.
one more time.
Hi, doctor. I just had one question. This was with respect to the image where you showed two different amputees, and you showed that the prosthetic adapted to the amputees. I just had this question: do you face any challenges when you change the prosthetic from one patient to the other, and do you have to fine tune it in some way to adapt to different amputees? Is that something which has to be done, or does it do the patients test it out and they have to adapt to the prosthetic? How does that work?
Yeah, so the first step is finding out where the residual muscles are for getting a good signal. So to do that, we use ultrasound to sort of, for each individual, figure out where their muscles are. And then we put electrodes on where we think, and we get a really robust signal. And as long as we can get a robust signal and we've tuned it to that individual, we can do the same thing every time. So they come back and we just put it on and we're good to go. There's no tuning every time they take it on and off. But for each individual, there are differences, mostly because their muscle morphology are very different.
Got that. Thank you very much.
Okay, so let's move on to the last thing. Ideally, I would love to measure brain activity as people walk and run so that we can use it as a signal to input to exoskeletons and robotics. And to do that, one obvious solution that a lot of people try is let's just be invasive. Let's cut into the skull and implant something. I would love to not make something invasive. I would love to have something that's easier for lots of people to use. So when we think about brain-computer interfaces, there's a lot of work in this area. But our eventual goal is for using exoskeletons and prostheses. This is traditionally how a lot of non-invasive brain-computer interfaces have worked. You put up a lot of electrodes on somebody's skull, on their scalp, and you record that, and then you use machine learning or some other algorithm to figure out what their intent is, and then you can move sensors. When I first got involved with EEG, everybody said, well, you can't do it during walking because there's too much motion artifact. And I was naive enough to say, well, let's try it and see what we can come up with. And so what we have figured out over the years is that, number one, it's better not to use electrode signals or channel signals, as sometimes they're called in the field. So imagine that this is a series of EEG electrodes on the scalp of a user. If I record from any of these electrodes, these channels of electrical signal, it is a amalgamation of all of the brain activity that's going on, right? And so if many brain areas are active, you're picking up all of the different signals. And so, number one, we take our EEG channels and we use ICA to create an unmixing matrix so that we can separate out extracted sources from different brain areas. That tends to be very helpful to separate out all of the signals that are happening in the brain. If we start with, say, 223 good electrodes, then we get 223 sources with ICA somewhere in the brain. And that's represented by this image that shows you with an MR magnetic resonance image of a person's anatomy. We can actually identify where these sources are coming from using an inverse head model. To reduce some of the noise, we've designed our own dual electrode system. If you've ever used a Bose noise canceling headphones, you know that they have one sensor that senses ambient noise, and then it inverts it and subtracts it from the signal, so you get a cleaner reproduction of music. We do something similar. We have a normal EEG electrode in red that's mounted on the scalp to record brain activity, and it also picks up motion artifact. And then we take a second EEG electrode, we invert it, we mechanically couple it to the first electrode, but electrically isolate it so that it's only motion artifact. So if I know what motion artifact looks like by itself, it's easier to remove motion artifact from a combination of brain activity and motion artifact. And then how do we know it's actually happening? So I'm a big believer that you should always question your data. How do you know it's real? And when we started to get a lot of brain dynamics, we're like, well, how do we know that's really what the brain is doing with our EEG electrodes? So we started building head phantoms. This is a electronic brain embedded within a skull made out of dental plaster and brain matter made out of ballistics gel that's has salt added to it, so it's conductive. And with this, we can make more complicated phantom heads. So Natalie and Ryan were postdocs in the lab that created a whole array of various phantom heads with different number of sources so that we could see how well our system is actually recovering the real brain signals. Of course, with EEG, a main problem is hair, so you have to throw in hair to make it more difficult to get the signal. And then we put IMUs, inertial measurement units, on somebody's head to record how they're moving, so that we can then take our phantom heads, put it on a robotic motion platform, bounce it along, and create motion artifact. So what you see in this first column are 8 different channel level signals. So this is each EEG electrode of 8 different electrodes. And you can see that it's a very noisy signal. After we subtract out the noise that we've separated because of the dual electrode and because of ICA, you get a way cleaner signal that you can use for figuring out brain dynamics. And in fact, when you compare your recovered independent component with the original phantom source, you actually, we get correlations greater than 0.9. So this to us was validation that what we're doing is really reproducing brain dynamics. So we've done a number of studies over the years. This was one where Andrew Norden, who was a postdoc in the lab, who's now at Texas A&M, was looking at how people respond to jumping over obstacles. And we did it at a range of different speeds. So On the far left is 0.5 meters per second, and then increasing speeds up to a 2.5 millimeter per second run. And what you see on each of these graphs is on the x-axis time. The vertical lines are when the object first appears, so it becomes on the treadmill, when it's directly under the person, and then when it goes off the treadmill. So in a slow walk, there's much more time here, several seconds, than there is on the 2.5 meters per second. This is less than a second. It's like half a second for this to happen. And on the y-axis is the frequency content of the brain signal. In this case, we're looking at premotor cortex for theta, alpha, beta, gamma frequency ranges of EEG spectral power. And what I want to show you is that if you look at slow walking and fast running, we're pretty much getting the same signal all the way through. It's an increase in spectral power that occurs in the premotor area when the object first appears. And then it looks longer here because time is stretched out compared to here. But we get relatively good signal quality for walking and running at a range of speeds. We've, over the years, come up with other alternatives. One of our recent algorithms is called I Can Clean. It actually does a really good job at CCA to try to clean up the data using the noise signals, the noise electrodes that we have. So this is our final clean EEG of somebody walking on uneven terrain. Here's the raw noise, the projected noise components on different channels, and the raw EEG. It works quite well. How does your brain actually respond to difficult terrain walking? So we looked at flat, low, medium, and high. And what it amounts to is higher blocks and a more uneven surface. And what we can show is that there are very key brain areas, including posterior parietal cortex and the sensory motor cortex, that show much more active involvement when you're walking on the uneven terrain. So in this particular instance, we're looking at the beta range and the alpha range a little bit more in posterior parietal and sensory motor. And the blue versus the time. So this is right heel strike, left toe off, left heel strike, right toe off. This shows us that there is a recruitment of more neurons and more brain activity on the uneven terrain surface in sensory motor cortex and posterior parietal than when they're walking on the flat surface. We're also interested in things that are not locomotion. So Amanda Studnicki just finished her Ph.D. recently with NSF funding to look at how people play games like table tennis. So you have to track with your eyes the ball, you have to intercept it, you have to move your body to intercept. And she had some really cool findings that have all come out in papers recently. Number one, take-home message, I would argue, when you play table tennis, a lot of your brain is involved. So these are the different brain areas that all showed strong activation playing table tennis. It's not just sensory motor cortex, but it's left cingulate, right cingulate, supplementary motor, parietal, occipital, cuneus. And if we look in on a given brain area, in this case, we're looking at parietal, what you see is versus time on the x-axis. 0 is when you're getting served at. And then the second vertical line is when you hit the ball back. You see this very characteristic recruitment of brain areas responding to the serve at you. And then you have what is known as this post-motor rebound, shown by the strong red. When you play a human opponent, it's very different than if you play a machine opponent. You get a much stronger activation level in both sensory motor cortex and parietal cortex when you're interacting with a machine than when you are with a human. We had originally tried to do tennis, and I wish I could say that we were successful, but we were actually having many problems with the serve of tennis, where you're looking up and you snap your head down really quickly. It pulled on the cables to the point where we really couldn't get clean signals, even though we ended up collecting a fair bit of data. Eventually, we moved to table tennis, and I point this out because there are still limitations. We can't do everything we want to do, but we're getting better. So, in the big picture of things, what do I want to leave you with? When you're thinking about merging humans and machines and getting to where we want to be in science fiction level, number one, change your framework. Think of it as not as a humans controlling the machine, but that there is an exchange in this symbiosis, both mechanical and electrical. And that when you're trying to better understand how any of this works, don't be afraid to go back to the mindset, let's perturb the environment or perturb the body or perturb the brain and look at how that changes the interaction amongst all three of them. And I got to give credit to all the people that did most of the work, and thank my funding sources, NIH, NSF, Congressionally Directed Medical Research Program, ARL, and Lockheed Martin. Thank you.
So I thank Professor Ferris for a great presentation. We have a few minutes for questions. Anybody? So did you try other sports, like other than tennis and ping pong? Did you try,
So we can do walking and running fairly well. We can do table tennis well now. I think we would have a better chance at doing tennis from everything we've learned over the last 4 years with table tennis. I would love to be able to do volleyball. I would love to be able to do football or soccer. Ultimate Frisbee is probably my next really big one because it's much larger framework and you have a lot of clear successes and failures, right? You're doing a throw of the Frisbee so you could monitor brain dynamics of the thrower and get their perception. Did they think it was a good throw or not? You could look at falls and when they knew they were falling and when they made the decision to lay out and jump. You could do catches. I tried to catch it and I missed. What part of your brain is responding and how fast you realize you missed that catch.
Questions?
There's a lot of research on EEG and golf putting because golf putting is so stationary. That's where people really started because they knew there wasn't going to be much motion artifact. But I think as we get more and more advanced with the hardware and signal processing, eventually any sport will be fair game.
So one other thing I want to ask is, do you have data about individuals like that lost maybe a limb, and the data that you have is before and after? Do you have data on that?
Yeah, so we're in the middle of analyzing it now. So I really am curious to the learning effect. This is why I got into EEG to begin with. I really wanted to study learning and how it changes the dynamics of what's going on in the brain. I don't have anything right now, but hopefully, give me another year and we'll have a bunch of papers published.
Here, I think.
Thank you, Professor. I just had this question. You did mention about tennis that when the person tosses the ball and you have a problem because the head looks up, would it be okay if the person tries an underarm serve and then try to figure out how the rally progresses with that? Would that be probably a good way of checking?
Absolutely. I think that would be great. So a lot of our table tennis data is now published in a database so other people can analyze. So, if you're looking for projects for undergrad, senior thesis, or master's student or PhD student that wants to try to play with this, we have a huge data set for table tennis that's available to anybody to download and analyze. So there's a lot of questions that could be explored along those lines.
And also, I had this other question. I wanted to know by monitoring people playing sports, what would be the application of this by monitoring how their signals are processed when they either serve or probably hit a backhand or a forehand? What would be the application of this? Some of the applications you did mention that it would help the person understand if it was a good forehand or a good backhand, or if it was a bad forehand or a backhand. But would there be any other applications of this study?
Yeah, for sure. And I'll try to talk you through a little bit. My mindset is, let's imagine that we can record somebody learning a sports skill and figuring out how they're doing it well and what changes, okay? Ideally, almost every type of therapeutic rehabilitation is trying to teach somebody a motor skill that they've lost and that we want them to get better at. Before we say, let's put all of this stuff on a patient and change their trajectory of their rehab, we need to have a theoretical framework to understand what is changing in the brain during that learning process. And one example that I give you is I have a grant proposal in review right now for virtual reality rehab. There's a lot of people around the world that want to use immersive virtual reality headsets to improve rehab, whether it be for spinal cord injury or stroke or multiple sclerosis or other things. We really have little understanding how virtual reality is changing what's going on in the brain. So by starting with humans that are physically and neurologically intact learning a sports skill, we can establish that framework, and then you can go say virtual reality. And I'll tell you right now, our data on virtual reality shows that you have a really hard time processing sensory information in virtual reality, because most of the time there's a lag between your visual and vestibular system in virtual reality. And so people don't learn as fast, and you can show that it's these different brain areas that are involved. So if you now take that to a virtual reality learning of a motor task in rehab, we know what the problem is, and can we better design virtual reality tech? And can we come up with better methods and games in virtual reality to teach somebody with neurological disability to relearn their skills?
Got that. Thank you very much. That sounds really interesting. That sounds really interesting.
Thanks.
Sai has a question as well.
Hello, Professor Dan. Professor, yeah, I'm also working on the BCI, and we just started working on setting up a specific BCI lab. So I have a question. When you are taking EEG signals in general, you worked on eliminating the noise specific to while the person is walking and doing any physical activity. Did you by any chance looked on the external noises like phone radiation and the Wi-Fi signals? All this can also make an impact on the EEG signals in general, right?
Absolutely. And so the nice thing is that the dual electrodes that we use are physically coupled to the main EEG electrodes. So they pick up all of that extra noise too. So not only does having that secondary electrode help with motion artifact, it helps with EMI, it helps with anything else that's in the area. And so we get a much cleaner signal using the dual electrode.
Yeah, and the second question is, since you also work with a lot of exoskeletons systems, in general, when you let's take a device which is having a lot of channels as well. So when you're recording the physical activity, do you think there would be any particular change when recording all the electrodes in general? I mean, all the channels, and those channels which are recording the motor cortex in the brain.
So my best answer, if I think I understand, is we have done sort of like down sampling of our electrode arrays to find out how many electrodes we need. And I don't think you really need as many as we use. We sort of do an overkill because we want to increase our resolution as best we can. But I think if you wanted to build a functional system that was as lightweight and as low cost as possible, you could definitely get away with much smaller numbers. And I think eventually we'll probably go in that direction when we try to develop technologies that are portable and actually sellable as a product.
Yeah, I would agree with your vision of non-invasive devices are much better than compared to the invasive devices, considering all the surgical procedures and all this stuff. Okay, my question is, when you look in, the invasive devices, their methods of acquiring more data in terms of ECOG, MEA, and DBS, did you ever try to, bridge down the gap between the non-invasive and invasive devices using your techniques?
We haven't yet. We'd like to do that. I have some collaborators and friends here at Florida that do invasive work. And I think it'd be really interesting to do a comparison and see how well they work together before we made decisions for any given different use for an application.
Okay, thank you, Professor.
Pauline.
Yeah, Professor, I was wondering, you said that these prosthetics are not being readily used, so you've not collected enough information. So is there anything to learn from the other types of prosthetics that are not bionic?
Yeah, so we actually do. So most of our subjects that we test with bionic prostheses have a standard passive device that they have been prescribed that they use on a regular basis. And so I'll give you one example. One of our ongoing experiments is actually recording the brain dynamics of healthy controls, individuals using a passive prosthesis that are amputees, and then those same individuals using a bionic prosthesis, because we want to know, what is really changing in terms of the biomechanics, the energetics, and the control with an amputation, and then how does the bionic device change it in addition. So there's definitely something to be learned. I think it just comes down to the reality of the funding world we live in. It's much easier to convince a reviewer if you're using a gee whiz, oh my God, that nobody's ever done that before type of study with a bionic prosthesis than you are trying to say, well, we want to understand how people walk with their normal prosthesis. You just don't get the extra bonus points from reviewers at NIH or NSF.
Okay, thank you.
Awesome. Any other questions? All right. Well, if not, let's thank Professor Ferris again for the first presentation in the MaLaMoBi series of this term. So it was great to have you here. Thank you very much.
Thank you. I appreciate it.
Thank you. Thanks a lot.